Hello everyone, welcome to this second live session for this course Introduction to Algebra Theory. Today we will try to solve some more questions based on what has been covered in the previous lectures. Let me share my screen. So let me start by yeah. The first question. Let's look at the first question. So define character of a group G in a field F. So and what are the all possible characters for the group S3? So first we need to see what do you mean by a character of a group in a field F, and then what are the all possible characters if I fixed a group G, let's say S3. So you all can think for a minute. Okay, so let's discuss the solution. So um, a character means you mean that phi from G to F cross. F cross means F minus 0. That becomes group under multiplication. So the map, if it is a group homomorphism, then we say it is a character of a group G. So we say character if you have group morphism from G to F cross group under multiplication, removing a zero element from the field. Now, looking at the definition and looking at the group now, S3, which has represented in terms of its generator, A and B are having certain relations among them. So can we use this representation of this group? Let's know the presentation of this group in order to find the characters or possible characters. You can think for some minutes. Maybe we can wait and then we'll discuss the solution. So let's discuss now the solution for this. Okay, so knowing the group S3 is nothing but all those AB such that A cube is 1, B square is 1, B inverse, B inverse. One can see from there that the elements of this group are 1, A square, and then B, AB is 3 elements in this group. That also know the group Xn has very many elements. So now, as you can see, element is or its power of B, or it is product of powers of AB. When you have generators, that any element you can write in terms of product of its generators, product of powers of generators. and use the definition that it's a homomorphism. So it's enough that you will define on its generators. If we need to define, let's say 5 from S3, and we are fixing our field to be C. So we are trying to define maps from S3 to C cross. Now, one has to know where A and B goes. This is what we need to know. Once we know this, then we know the group, the homomorphism fully. So you can think where A and where B can possibly go, knowing that there are relations for A and B. Relations, let me repeat, this is relation for A, this is relation for B. So please think for a minute. All right. So you know that AQ identity and identity has to be preserved under morphism. So therefore, phi A Q, which is phi at, let's say, identity, is numbered 1. Now, phi use the homomorphism that phi A cube is 1. So now, here note that phi A has the choices for which its cube is 1. That means phi A has to be cube root of unity. These are the possibilities that may have using the relation that A cube is 1. Now we will use few more relations. We are given that B inverse AB is A inverse. I'll highlight. So B inverse AB is A inverse. And knowing A cube is 1, that means we have A into A square is 1. That means A inverse 2 power of A. That means you have, and also from B square is 1 implies B is B inverse. So you can simply write that BAB, or maybe like AB as B and then A inverse is A square. From here, knowing that B cannot be a zero element, this relation is enough. Okay, let's not bother about what A and B are. Let's come to use the fact that AB is B A square. Now phi of AB, if equals to phi B A square, I will simply use homomorphism map and then I will write like this. I can write like this. Now you know that B cannot be 0. Phi B cannot be 0. Right? Because we know that B square is 1, therefore phi B square is phi B whole square, which is 1. Therefore, phi B has two possibilities. It's a root of this. It's a two root of unity. Let's say it has to be either plus or minus 1, right? So of course phi B cannot be 0. So I simply cancel phi B, and therefore from here I will get phi A equals to 1. Why? Because phi A cannot be 0, right? Because we are not using, we cannot map to 0, right? Because we have anyway excluded 0 element from the field. So phi A has to be 1. Earlier we had phi A cube is 1, but not just that, we more precise condition. That was just saying that it should be a cube root of unity, but there are 3 cube roots of unity other than 1. So now the upshot is, okay, here is the upshot. So phi A goes to 1. This we say that the under phi map A goes to 1. And we see that from here that phi B square is 1. That means phi B has plus minus 1 two possibilities. Right. So let me just these things that we have, or maybe we will keep. So thus we have phi 1 going to 1, B going to 1. It's a trade. Going to 1 and B going to 1 and B going to minus. This we say as a sign. Its name is sign. It's a sign character. Sign is because all element inside S3 will be a transposition, and it's a odd length cycle, right? So therefore, cycles have their signs based on whether it's a even permutation or the odd permutation. If it is odd, then we have -1, and for even we have plus ones. Therefore, we call it as a sign character, and this is nothing but a trivial character. So the upshot is we have total 2 characters. Yeah, so maybe we pause for a minute and you can let's just digest what we did, or maybe I'll repeat. So in order to know homomorphism from your group to, let's say we have fixed this field C, we want to define, if you know the group well in the sense you know its generators, then it's good that you define your map only on the generators and see the relations among generators. Relations, there will be certain relations, right? Because you are working on finite group. So orders, some orders will be finite, and order of every element will be finite. In particular, your generators have finite order, and there will be certain relation among them, how they are related. These things will help us to define the map. And here we have 3 relations. A power 3 is 1, B power 2 is 1, and B inverse A, B inverse. We will use all these relations to get that where possibly A and B can go, knowing that A and B are the generators of this group. Only one possibility, we have 2, and therefore in total we have 2 homomorphism. One is trivial, one is non-trivial. So therefore, total number of characters for group 3 are only 2. Yeah. Okay, now let's go to question number 2. We have 2 fields and K, let's say, and we have sigma 1, sigma 2, sigma n. From K to L, we field homomorphism. So given this information that fields are given, we have field homomorphism, let's say possibly n. What is the fixed field of sigma 1, sigma 2, sigma n? That means what are all those what are all those elements of K? So first of all, okay, let's maybe one has to say what question. Okay, part 1 says one has to define what is K, sigma 1, sigma 2, sigma n, or maybe the same notation which in the notes we have used is a set of field homomorphism from K to L. It's a field homomorphism, and we are looking at the fixed field of S under this K. So we must have seen this definition. So I'll wait for a minute and then you think of it and you write on yourself, and then we can read the solution. All right. So you might have thought about by now that this is nothing but all those elements alpha in the field K from where your sigmas are defined. This is the domain set. All those elements from K which are being fixed under a very such field homomorphism. That means sigma 1 alpha is same as sigma 2 alpha is same as up to sigma n alpha. And this all sigma should fix that alpha. Right? So all those maps, all those elements of K which are being fixed by all the homomorphism that has been given. Right. Now, knowing the definition, now we have to go to question part 2. Part 2 says if you are given K to be 2 by 4 and L equals to C. First one has to find what are all possible homomorphisms, field homomorphisms from K to L. This is the first question. And then you take the set of all sigma i's, let's say S, and you try to find what is K power S. This is the question. So think for a moment that how to see all possible field homomorphism from K to L. Now, looking at the field, K is nothing but the small field. Right? It's the smallest field containing both Q and 2 power 1 by 4. So, knowing the same idea that we saw for groups, it's enough to define on the generators. Q and 2 power 1 by 4 generates this field. Therefore, it's enough. Where every element, let's say A, if A is in Q, where does A goes? And where does 2 power 1 by 4 goes? Right. So knowing one factor that these fields contain Q is a characteristic zero field, and therefore their prime fields are nothing but Q. And we know that for any field homomorphism, prime field is always being constant under any field homomorphism. Right? If you have any field homomorphism which has prime field, let's say here it is Q, then prime field will be constant by that field homomorphism. And Q is that, therefore A goes to A. Every element of Q will be fixed. It's important where this 2 power 1 by 4 goes. Note that by 2 power 1 by 4, if I raise its power 4 times, this is same as 2 power 1 by 4 raising power 4 times. But that is nothing but 2. And 2 is an element of Q. It will be kept constant. Therefore, what you got is 5 2 power 1 by 4. Its whole power 4 is nothing but 2. That is, what are the all possible choices of 5 2 power 1 by 4? So remember, it can seem like this. Sorry, 2 power 1 by 4. Right, so 2 power 1 by 4 actually has 4 choices. It has 4 choices. 2 power 1 by 4 minus 2 power 1 by 4, 2 power 1 by 4, I, and 2 power minus 1 by 2 power 4 I. Why? Because these are 4 roots of unity. Roots of unity are nothing but plus minus 1 plus minus I. All these elements get multiplied by 2 power 1 by 4 and we get all choices. So in this case, we have total 4 field homomorphism from K to L. Now, let me write this 2 power 1 by 4 going to 2 power 1 by 4 as sigma 1. 2 power 1 by 4 going to 2 power minus 2 power 1 by 4 2 times I sigma 3 and minus 2 power 1 by 4 at sigma 4. Let's see. Right. Now, if we look at the set by all these elements, sigma 1, sigma 2, sigma 3, sigma 4, we want to know the fixed field of K raised to the set containing all 4 sigma i's. Can you think for the element or sorry, all field homomorphisms? Sigma 1, sigma 2, sigma 3, and sigma 4. Yeah. Okay. Now let me write it down. I'll just remove this part which has been so let S is sigma 1, sigma 2, sigma 3, sigma 4, and we want to know Ks, that is alpha in Q2 power 1 by 4, such that sigma I alpha is equal to, let's say, sigma alpha sigma J alpha for I J from 1 to 4. Right. So, not that it is typical element of this field Q2 power 1 by 4. This is first thing. So for that you need to know, because you know every extension, field extension is a vector space over the base field. So Q2 power 1 by 4 over Q actually is a vector space, and dimension will be the degree of its extension. Now as we know, the degree is nothing but, because this is a irreducible polynomial over Q, therefore degree is 4. Now, first here one has to see what is the basis. Basis will be 1, 2 power 1 by 4, 2 power 1 by 2, 2 power 3 by 4. This is a basis. How? You will just simply see 1 which is generated by 2 power 1 by 4. So, if you write it is like 1, 2 power 1 by 4, it's 1 power. You raise its 2 power, it will be 2 by 2 by 4, 2 power 3 by 4. This is nothing but 2 power 1 by 4, and then you will get 2, but which is anyway combination of 1. So therefore, this is the basis. Now, knowing the basis, every element you can write as A0 plus A1 2 power 1 by 4 plus K2 2 or 2 by 1 by 2, K3 2 power 3 by 4. Now one wants to know, if I apply sigma 1, let's say. Sigma 1, we know that it will not change anything, right? Because it is keeping every element. In fact, the generator also itself, it is kept constant. Sigma 1 will not change anything. We will see what sigma 2 does. Remember what is sigma 2? I'll just highlight. This is sigma 2. This is sigma 3. This is sigma 4. This is just identity, you can see. If you see this is an element from Q, so of course AIs are over Q because the base field or constants will be from Q. Now, if I apply sigma 2 to this, A0 will be kept constant, A1 will be kept constant, 2 power 1 by 4 goes to minus 2 power 1 by 4. A2, 2 power 1 by 2. Where does that go? You know, why I'm saying that 2 power 1 by 4 is enough to know, because 2 power 1 by 2 is 2 power 1 by 4, it's a square. Use the fact that it's a homomorphism, and then we will use that it's 2 power 1 by 4 whole square. Enough to know on this. We will just square that. It is minus 2 power 1 by 4 whole square, which is 2 power 1 by 2 only. So it will be remain same. However, 2 power 3 is nothing but 5 2 power 1 by 4 whole cube. Now, if you have 5 2 power 1 by 4 as minus 2 power 1 by 4, then its cube will be a negative of 2 power. You can see, right? We want to set the same as sigma alpha, but sigma 1 alpha is like it is same. Your alpha 1 by 4, 2 power 1 by 2, 3 by 4. Comparing this, you know that 2 power 1 by 4, 2 power 1 by 2, 3 by 4, this set is a basis. Basis means linearly independent set, right? Then constants has to be 0. If you compare these two, you will get that A1 is 0, A3 is 0. From here and from, because you get, if you take equate both, then A0 and A2 will get, A will get cancelled, just you will remain the A. You know that A1 and A3 both have to be 0. Let me write this up short now. So we got A1 and A3 from 0. If I write my alpha to be A0 plus A1 by 2 to 1 by 4, 2 to 1 by 2, A3 2 to 3 by 4. A1, A3 are gone, then my alpha is just remain like this. I will write like this. Now, if this was just by sigma 2, let's see what sigma 3 does. Sigma 3 alpha should be same as sigma 1 alpha. Sigma 1 alpha will keep it is like it is, sorry, keep this as it is. Sigma 3 will use my 2 power 1 by 2. Right? So, sigma sigma 3 at A0 plus A2 2 power 1 by 2 is it should be like this. This we want. What are those aspects for which sigma 3 kept? Sigma 3 keep this element constant, right? Let's look at this again. Sigma 3 2 power 1 by 4 whole square is nothing but sigma 3 2 power 1 by 4. Right? This is because of homomorphism. If I square the 2 power 1 by 3 goes and 3 2 power 1 by 4. Here it will go. So this square and this element goes to 2 power 1 by 4 I and its square is nothing but 1 by. But what is this element? This is minus 2 power 1 by. So therefore, the whole thing will go to A0 minus A2 2 power 1 by 2, which is has to be like this. But if we compare, what we will get? We will get A2, right? Because it's a basis element. If some trends have to be zeros, if it is 0, then it is 0, right? So therefore, I got A2 to be 0. A1, A2, A3, all right. So let me just remove the things from this page. It's so messy. Yeah. So I read once again. So looking at how which was our general element was like this. Here we get that though in K such that sigma alpha equal to sigma J alpha. This is just of the why? Because A1, A2, A3 all are 0. But A0 is nothing but the set of Q, right? It's all A0, A0 and Q. This is all QLS. Therefore, KS is equal to Q. So maybe we will wait for a minute. All right, so I think all of the things must be clear by now. Now, okay, page again. We have to find out the fixed field when I keep my L to be K. Earlier L was C. You mean we were finding all out homomorphism from C. Homomorphism, field homomorphism from K to K. That means they will be automorphisms, right? So now one needs to find all possible homomorphisms. Let's say, but sigma is from K to K. These are field homomorphisms. And where is K? K is 1 by 4. So now this time we don't have C. We only from Q 2 power 1 by 4 to Q 2 power 1 by 4. Where is first of all A goes, where A is in Q? Where does 2 power 1 by 4 goes under any field homomorphism? We saw for previously that any field homomorphism, suppose let's say sigma here, sigma any field homomorphism, it will take power to be 2. This is off. Therefore, sigma 2 power 1 by 4 is 2 power 1 by 4 times e 2 pi I k by 4, where k is 0, 1, 2, 3. And that we saw this set was like this. Just right. Once again, this was a set of possibilities where 2 power 1 by 4 can go. But in this case, we cannot go beyond this field. We have to keep the images inside this. So what among these four, what are allowed in map 2 by 4 to power 1 by 4 under any. Notice we have two real roots, two imaginary roots. And this field does not contain imaginary roots. This is a real field, right? Therefore, 2 power 1 by 4 either goes to this or goes to this. However, A is kept constant because it's an element of Q. Q is a prime field here. So how many homomorphisms we have? Sigma 1, which is Q 2 power 1 by 4, Q 2 power 1 by 4, Q going to Q, power 1 by 4 going to 2 1 by 4. This is like identity. Sigma 2 from K to K, Q going to Q, where Q is an element of Q. And 2 power 1 by 4 goes to minus 2 power 1. This is our set of. So we field L. Here L is K. If you change the field, number of homomorphism changes, right? Earlier we have 4. Now we have 2. Now, what is KS? So what is a fixed field? Two field homomorphism on K. That means what are the all elements alpha in 2 power 1 by 4 such that sigma 1 alpha and sigma 2 alpha both maps to the same element. Again, I'm just repeating, any alpha which we saw has to be like A0 plus A1 2 power 1 by 4, A2 2 power 1 by 2, A3 2 power 3 by 4. Right. This is our general element from Q 2 power 1 by 4. By looking the field as a vector space over Q of dimension 4. Now let's say we know that sigma 1 does not change anything. Sigma 1 alpha will remain as alpha. Let's apply sigma 2 alpha will map A0 to A0, A1 to 2 power 1 by 4 to minus 2 power 1 by 4, and where will A2 2 power 1 by 2 goes? Notice 2 power 1 by 2 is sigma 2 under the map sigma 2 power 1 by 4 whole square. But this is minus 2 power 1 by 4 whole square is same as 2 power 1 by 2. So 2 power 1 by 2 is constant under sigma 2. However, you will see that it is sigma 2 of 2 power 1 by 4 cube is negative of minus 2 power 1 by 2. Because of the fact that sigma 2, 2 power 1 by 4 is minus 2 power 1 by 4, and therefore if you take the cube of, and it will be minus 2 power 3 by 4. Yeah, so I'll just remove all these side calculations. So what we got is exactly like this. And we want to say that A0 minus A1 2 power 1 plus A2 2 power 1 by 2 minus A3 2 power 1 3 by 4. This has to be same as sigma 1 alpha, but sigma 1 alpha is same as alpha. That means A1, because identity map does not change anything, it will remain alpha to be alpha. A3 2 power 3 by. Compare A0 get cancelled, A2 A2 get cancelled, and we will be left with twice A1 2 power 1 by 4 twice A3 2 power 3 by 4. This is 0. But you know, these are the nothing but this is a linearly independent set. So because subset of linearly independent is always linear. Therefore, 2A1 is 0, 2A3 is 0, and therefore A1 and 3 is 0. So any typical element, if I have alpha is A0 plus A1 to power 1 by 4 3/4. These are the elements which are, let's say, kept constant. Therefore, among them, even if we have to be 0. And this is nothing but all possible elements like this. But these are, of course, where we not take both are in Q. Can you see this field as something? Because this is the fixed field. Fixed field. Therefore, it has to be a field. Can you see this as a field? Can you write this as some known field? Think for a minute, you will get it. It's nothing but Q over 1/2. So getting back, this is the fixed field is Q. This is the here it is Q to 1/5. I'll pause for a minute. See the solution once again. Now, going to this question. Yeah. Given K to be Q root 2K, and you have to find all possible field homomorphisms from K to K. Again, K to K. And check whether there are really four field homomorphisms or more or less. You have to check. Actually, you have to prove there are four only. And then you have to find the fixed field corresponding to certain sets. Here, it's S1, S2, S3, S4, all are distinct. And we will see based on the sets how the fixed field changes. Right? So now at least we understand what is going on in the question. So let's try to do something. Right. So you have to find first of all sigma from Q root 3 to Q root 2 root 3, all possible field homomorphisms. Again, notice that these are the smallest fields containing Q, root 2 and root 3. So it's enough to define the map on Q and where does Q goes? Q will be constant in Q. Where does root 2 and where does root 3 goes? Think for a minute. Again, your phi root 2 you want to know. Maybe sigma we have used sigma. Sigma root 2 we want to know. But we also know if I square it up, this is nothing but root 2 root 2. This is nothing but 2. But 2 is an element of Q. Therefore, wherever sigma root 2 can go, its square has to be 2. What are the possibilities for sigma root 2 then? Notice only 2. Plus minus root 2. So we got plus minus root 2. Same idea will give you there are plus minus root 3. One possibility is root 3 can go to root 3. Other possibility is root 3 can go to minus root 3. This is the meaning of that root 3 can go to two possibilities plus minus root 3. Now, can you see now how many homomorphisms that you have? So if I try to see from K to K, how many? It's 4, right? First one is root 2 going to root 2, root 3 going to root 3. Everything goes to the same identity. Other one is root 2 go to minus root 2, root 3 is constant, let's say. Other is root 2 is constant, but root 3 going to minus root 3. And the final one is root 2 going to minus root 2, root 3 goes to minus root 3. Right? Now, suppose we consider this to be a sigma 1, sigma 2, sigma 3, sigma 4. So indeed we have set is indeed containing 4 field homomorphism. This has been. So what is the other thing that we need to see is the fixed field at certain sets which do not contain completely all homomorphisms. Maybe let's say the set S1, if you look at set S1, K, sigma 1, sigma 2. This is my set S1. So if I try to look at this set, what are the elements of K which are being fixed by all sigma 1, sigma 2? Yeah, this is the question. So just highlighting, this is sigma 1, sigma 2, sigma 3, and sigma 4. Right, we have these many. Now, if we look a general element of K, K means Q root 2. Notice it has the basis like this. 1, root 2, root 3, root 2, root 3. Any element of this field can be written as a combination of these elements itself. Right. So therefore, we will simply write any element alpha in K as alpha is. So let me write the definition first. This is set of all those alpha in K such that sigma 1 alpha is the same sigma 2 alpha. Only two. Can be written as A0 plus A1 root 2, A2 root 3, and then product of root 2 root 3. Right. Now we know that sigma 1 does not change anything. Sigma 1 alpha will be alpha. Let's look at sigma 2 alpha. So sigma 2 alpha will be A0 will go to A0, A1. Remember, this is my sigma 2. It will map root 2 to minus root 2. So this will be minus A1 root 2. Root 3 goes to root 3, so plus into 3. But this will be again negative A3 root 2 root 3. And we want to say sigma 2 alpha, same as sigma 1 alpha, which is nothing but alpha itself. Now, can you compare these two things? A0 get cancelled, A2 get cancelled, and we are left with twice A1 root 2, twice A3 root 2 root 3. Knowing that this is a linearly independent set, which you are making it to 0, so A1 is 0, A3 is 0. Is it okay? Right, A1, A3 is 0. What is left now? Okay, from alpha. Now I'll rub it. I will just remember that A1 and A3 were 0. So A1 0. We will write like this. A1 is 0, we can remove this, we can remove A3. So it is all those alpha in K which looks like alpha is A0 plus A2 root 3 because in A1, A3 was 0. And can you see this field where A0 is off from Q? Can you this set as some field, known field which you know? Yeah, it is Q root 3. Right? So therefore the first one, the fixed field is Q root 3. Right? Similar way you can see for any set which contains two elements. You can see the answer. Maybe I'll write the answer. You can verify this Q root 2. Okay. Look at sigma 1, sigma 2, sigma 3. This set. We will discuss this third and fourth part now. Okay, now I will change my definition of we'll add a page and we will do the calculation there. Okay. Right. Now we have all the set and we need to find what is K of S3, which is sigma 1, sigma 2. We know what a sigma is, right? It's a set of all those alpha in Q root 2 root 3 such that sigma 1 alpha is same as sigma 2 alpha is sigma 3 alpha. And in fact, you can write sigma 1. Of course, if you fix your first to be always identity, because identity is always there, or then you can simply change this to this. Always map elements. So you can actually write this part also as the fix. Right. Now let's look at what is alpha. Alpha is, we remember that this is 1 root 2 root 3 a3 times root 2 root 2. Now let's look where sigma 2 can go. We recall that sigma 2 we saw for this case, for first part, sigma 2 made sigma 2 changed, or maybe under sigma 2 and equating to sigma 1 from case 1, right? From just now we saw A1, A3 becomes 0, right? So we use this back now. So sigma 2 alpha equating to alpha implies A1 is A3 is 0. Our alpha has been reduced to only this, only like this. From this, we can see where is sigma 3 maps this to. Now, sigma 3 maps to A0 plus A1 root 2 like A0 will be fixed, right? Look at sigma 3, there is root 2 maps. Sigma 3 maps. Maybe we will see once again. Q root 3, right? So A1, I guess. Yeah. A1 3 0, that means our element is left with A0 plus A2 root 3. I'm so sorry. This is like alpha, which has been reduced by mapping sigma 2 sigma equal to alpha, right? Only using this fact, only using this. Because we have to equate anyway all, but if you use this fact only, then we got A130 from previous case. Now, let me apply sigma 3 to alpha and equate it to alpha, which is A0 plus A2. A0 will go to A0, root 3 go under sigma 3, it will go to minus root 3, right? So A2 minus root 3, same as A0 plus A2 root 3. A0 cancel to A2 root 3 is 0. What can we say about A2? Again, A2 is 0 because root 3 is a linear number. Or of course, from here it's because root 3 and root 1 is 0. Maybe various reasons to say that A2 is 0. Right, so okay. What we got is A1, A2, A3 all in 0. If we want to say what is alpha such that sigma 1 alpha is same as sigma 2 alpha is same as sigma 3 alpha. If we look at this set, then alpha is only A0. Okay, maybe I'll write completely. Alpha is like this. Yeah. A1, A2, A3, all are 0. Then only it will be kept and constant by sigma 1, sigma 2, sigma. But for that, it is just left with A0, where A0 is in Q, therefore it is just Q. Right? Therefore, I will just write this is Q. And if a subset gives me a prime field to be fixed, then set S4 will also give me Q that you can see yourself. That's a simple fact. Smaller it is Q, then of course nothing small can be fixed, and therefore S4 will fixed, right? So these are the answers for this question. I think everything is clear. So we will go to question. We'll hide first the solution. Let's think about the question first. Okay, question is, recall there is a theorem in our lectures that if we take sigma 1, sigma 2, sigma n from K to L distinct, remember distinct field homomorph, F be their fixed field. F is the fixed field. That means F is nothing but K set containing S1, sigma 1, sigma 2, F sigma. This is the meaning of F is the fixed field. K to F is always greater or equal to N. That means the dimension or the degree of your K is to F is either greater than or equals to your set, the cardinality of your set. I think this, the way it has been mentioned in the class is like K to Ks, cardinality is greater than equal to mod S. Right? So we want an example where this inequality is strict, and also we want an example where this inequality becomes equality. We want two examples. Can you use the previous question to obtain an example for field K and L and a set? You need to find three things. What is the field K? What is the field L? What is the set S? Then only you can tell the three things, right? The degree of your extension field is greater than equal to the cardinality of the order of the set. If you see, maybe let's we go here. Notice that, let's say in first part itself, when you have A sigma 2 is Q root 3. So what is the structure of the field now? Let's say this contains Q and this contained in K, which is Q root 3. This is what we have. Degree, you notice this is 2, this is 2. This gives me example that the set cardinality is also 2 and the cardinality of K is to Ks is also. So just by looking at the previous example, will give you one example of Ks where L equals to K, of course. We got three things such that what we want, the quality is being established. But can we find again some pair Ks and such that this cardinality K is to Ks is strictly greater than the cardinality of the set? Think for a moment, you will get from here only. I got the answer, and the answer is if you take this field and the set of three elements, look at the third point here. Third point has the sigma 1, sigma 2, sigma 3. Set cardinality of the set is 3, and the fixed field is Q. A is Q root 2 root 3, fixed field is Q, and the degree of this is 4. Looking at it out, degree is 4. However, the cardinality 3. So we have this is 4, this is 3. And you will observe there is one more comment that is mentioned in the lectures that this inequality is not equality because your set is not a group. That means if you take product of squaring the automorphism or something, you will do phi homomorphism on the set. That means it's not a group. So our next question saying that define gal first of all. Okay, I'll just put it off so that you will get some idea to think. Okay. Here you have to define first of all what is the Galois group of field extension. So suppose K over X is field what is the Galois group for that? This is the first question. What are the Galois groups of this field extension and this field extension? So think for a minute. Okay, so let me write down solution. So Galois group of a field extension K over F is the set of the group, in fact, group of all F photomorphism of K. What is the meaning of photomorphisms? That means if you take any homomorphism from K to K, sigma is A for all A. That means F elements are fixed by sigma. This is the meaning of photomorphisms. Now, I mean the definition. Now, the Galois group of Q to I. What Q we want to know? If I have Q, Q root. Look at the definition again. Think for a minute. What are all possible photomorphisms of this K? Yes. F is notice we want to define sigma from Q root to I to root to I. Automorphisms, you have to make this field. Question is, where does root 2 go? Where does I go? Q anyway have a fixed, we know that. It's a passive. So as we have earlier, root 2, 5 root 2 whole square is 5 2, which is 2. Therefore, 5 root 2 whole square is 2, implies 5 2 has from here, it's minus 2. Again, if you take I square is minus 1, phi of I is whole square is minus 1. Square, which is phi of minus 1 is minus 1 because minus 1 is an element of cube. So phi I square is minus 1, that means phi I square is plus minus I. Right? So plus minus I. Alright, so this, can you find what is the all Q automorphisms? Notice that what is the prime field here? Yeah, prime field is Q. Every automorphism will fix Q. But we also on which are those which fixes F is nothing but Q. That means we all want all such automorphisms which fixes Q, but we know that all automorphisms fixes Q because Q is a prime field. Therefore, Galois group is nothing but set of automorphisms where one is root 2 going to root 2, I going to I. Sigma 2 is root 2 going to minus root 2, I going to I. Other is root 2 going to root 2, I going to minus I. And the fourth one is root 2 going to minus root 2, I going to minus I. This will give you all four automorphisms and all such things is Q. But we want all automorphisms which are fixed by Q, but they, so for this, the Galois group is actually sigma 1, sigma 2, sigma. But as a group, its order is right. Order is 4. What can we say about this group? Can you identify this group of order 4? How many groups you by the way? Next, we will discuss this. So Here, the cardinality of this Galois group is 4, which is sigma 1, sigma 2, sigma 3, sigma 4. I'll write once again. Root 2 going to root 2, I going to I, sigma 1. Root 2 going to minus root 2, I going to I, sigma 2. Root 2 going to root 2, I going to minus I, sigma 3. Root 2 going to minus root 2, I going to minus I, sigma 4. Right? If you see carefully, there are two groups up to isomorphism of order 4 by fundamental theorem of abelian groups. Why abelian? Because any group of order p square is p is 2 here. This is an abelian group, and therefore it is isomorphic to either Z2 cross Z2 or Z5. This is a cyclic group of order 4. Which group do you think is the our group? Can our group, our automorphisms which we have, can they have order 4? Let's look at their orders. Let's look at sigma 2. Sigma 2 going to root 2 going to minus root 2, I going to I. If I look at sigma 2 square of root 2, then it is sigma 2 of sigma 2 root 2. Notice that the group operation is composition. Composition of maps. We are composing. Sigma 2 root 2 going to minus root 2, but minus root 2 will goes to 2. Sigma 2 square I is nothing but sigma 2I, which is I. That means sigma 2 square is identity map. The order of sigma 2 is nothing but 2. And you will see the order of sigma 3, order of sigma 4, all have order 2. Your group do not have any element of order 4. So which group it should be? Yeah, it will be Z2. So for this, our group is Z2 cross Z. Let's look at this other group. This is Q 2 power 1 by 3 over Q. So look at, add one more page. So we want Q 2 power 1 by 3 over Q, and we want the Galois group of this. It's Galois A over F. It is set of group of all F automorphisms of Q. Now can you see something? Of course, you have to define an automorphism. Q 2 power 1 by 3 to Q 2 power 1 by 3. You have to just tell me where 2 power 1 by 3 is, because Q elements are fixed. Right? Again, these are all simple facts that these are homomorphism. Therefore, this is 2. It's 2 because 2 is in Q. 2 power 1 by 3 is 2 power 1 by 3 e 2 pi I k by 3. K is from 0 1. So this is nothing but 2 power 1 by 3, 2 power 1 by 3 omega, 2 power 1 by 3 omega square, or maybe like this. These are all possible choices. But you know that these two roots are complex roots. This is the only real root. And your field is not a complex field. It's a real field. Therefore, this is the only possibility of your automorphism, which is nothing but your identity map. That means your Galois group is nothing but trivial group. Just trivial group. And it is on trivial group, right? So for this, the group is trivial. Okay, now next question. It says, question 6, in theorem 1, K is to F is greater than equal to S, and we saw is to Ks is greater than equal to mod S, where S is the cardinality n. Question is, when this inequality become equality? What is the condition for which you can say this inequality equality. You might have seen in your notes that this is only when your S is nothing but a group of automorphism, not just set of automorphism, but actually a group. Whenever it is a group, cardinality of your K is to fixed field is always the index of the order of the group, in order of the group, right? So as you can also verify the statement through our examples also, right? So I think till question 6, everything is clear. We'll go to question 7. Question 7 says, I just talk about all the solutions. So that you can think of yourself. Right. So I have read a few things. You may need it sometime. You have to check whether the following extensions to be Galois. There are 4 extensions. Some are over Q, one is over finite P. You have to check which of them are the Galois extensions. Not all are Galois. Okay, maybe I don't know. Yeah, you check yourself. So first of all, which extension? When do we say an extension is Galois extension? This is the first thing. Can you see that? Recall A over F is Galois extension if and only if A is F is cardinality of the group. And this group is nothing but it's a group of all F automorphisms of right. All right. Can you check all these things for? Let's check QI over Q. First, we know what is the degree of the extension. Because we will need this, we will be needing this. This is our K, this is our F. This is our K, this is our F, this is our K, this is our F, and this is again K, this is F. And you have to use this on the degree of your extension all the time. What is a degree? It's if you notice carefully, then I is the root of this irreducible over Q, right? This is irreducible. Therefore, the degree is not. This is okay, right? It's true. We need to check that if we look at all possible automorphisms for K to K, such that sigma is A for all A in Q. This is what the meaning of F automorphism. F is Q automorphism here. Right. Homomorphism, which is F. Is this set has the cardinality same as 2? This is the thing that we need to check. Let's look at QI to QI. How many automorphism, let's say, from QI to QI. Q is always mapped to Q. It's all important where I goes. Right? And remember, I square is -1. This is same as whole square. This is -1. So sigma I whole square is -1 and sigma is -1. Therefore, it is -1. So we have sigma 1, which maps I to I, sigma 2, I1 to -I. So we have sigma 1, sigma 2 to the homomorphism, which fixes Q that cardinality it is 2. So it is in extension. So this is Galois. This is Galois. Can you check for Q2 per 1/3? Is this Galois? Let's change the extension now. Change the Q2 per 1/3. First of all, what is the degree of this extension? Can you check? Notice that this x cube minus 2 is irreducible polynomial over Q having 2 power 1 by 3 as a root. Therefore, the degree of your extension is 3, the degree of your irreducible polynomial. Now, can you check the Galois group? Galois group, what is the cardinality of this group? That means you have to check all those cardinality of the set of all automorphisms from 2 power 1 by 3 to Q 2 power 1 by 3 such that sigma is a for all A in Q. The set and its cardinality you need to find. Right. So how many automorphisms? This has been repeatedly come. So 2 power 1 by 3 to 2 power 1 by 3. We have many roots. But among them, only 2 power 1 by 3 is the real root. So 2 power 1 by 3 can only go to 2 power 1 by 3. So we have just the identity homomorphism, homomorphism in the Galois group. So Galois group has just this. So cardinality is nothing but 1, which is not equal to 3. Therefore, this case it's not a Galois extension. I guess this should be okay. Yeah, let's go to third. Right. So we want to check whether this extension is a Galois extension or not. Think for a minute, we will discuss the solution. All right, so first of all, degree. So by structure theorem, you know that this is nothing but where f is a irreducible polynomial of degree r over fp. This we know by the construction, the way how we construct a finite field extension. So this degree we know by the way it has been constructed. This is we know. Now we want to know the Galois group of FPR or FP. That means all those field automorphisms from FPR to FPR such that sigma is a for all A infinite field FP. Right? Now, it's not naturally one can say that exactly it is. Yeah, so we don't know that. But let's look at some automorphisms that we can use. Not all can be directly what are all possible automorphisms. But let's see a group containing some automorphism. Okay. Let's look at some phi map from FP. I'm sending element x to x power p. X power p. I think this has come in the lecture. This is Frobenius map. What can you say about this map? Is it a field homomorphism? Field means you just have to check ring identity goes to identity, right? One goes to one, that you need to check that there is in fact. Um, you can also see that phi xy goes to phi x phi y. It's not difficult to see, but phi of x plus y is also equals to phi x plus phi y. Why? Because x plus y whole power p is x power p plus y power p, because when you expand this by binomial expansion, you have x power p plus p time everything plus y power p. Everything, whatever they have, they are the p characteristic of your field is p. Therefore, all these components become zero. Right. So it's the important fact is characteristic of FP is p. That makes you your job here that actually this is a field of. So indeed, this is a field homomorphism. Okay, if I raise its power, let's say if I raise its power 2, that means if I compose it twice, this is what the map will be, because the operation is composition. How the map will look like? Phi square x is nothing but phi of x power p, which is xp power p, which is xp square. Is that okay? Because this is xp into p, which is p square. All right, so if you keep doing this, you will get phi I x is nothing but xp power I. P raised to power will be the I raising power I to your field homomorphism. Can you say about phi r x? What is that? Notice it's xp power r. Something is important here. Can you notice that? Right. So they will write, okay, maybe I'll add one more page, we will do there. Yeah. So P power R to FP power R, we are having this map x1 to x power P. Moreover, every element FP power R, that is pi's the polynomial xp power R minus x. So this is again by the construction of the field, we know this. Therefore, if we look at phi, this is the phi map, phi power R power x. This is nothing but x p power R. But from here, you know that x p power R is same as x. If we have any element from your FPR, so this has to be x. This one. What did you get? You get phi R x is x. Actually, phi R is the identity. And indeed, you can prove that there is no such n. So there does not exist any n in n such that phi n is identity if n is less than r. Therefore, order of phi is r actually. Also, now you know, let's go to the group. Galois group of FPR over FP is nothing but it is the set of all automorphisms from FPR to FPR. We don't know fully, but we know full some of them. Some of them are nothing but 1, 5, 5 square, 5 power r minus 1, because r will be identity that we have taken in the first part. Okay, so we know this is a subgroup of group with cardinality r, right? Correct. But you know that there is one more thing that you know, that Galois group of K over F is nothing but, okay, maybe I read this way, Galois group of K over Ks is equal to, maybe I'll write not this way, K over Kg is, this is same as G, right? So now Galois group of FPR over FP, this index should be same as K is to K power Galois, fixed field of Galois. Now let's look at the field extension. We have K. K means here K is FPR, right? So we have FP, we have FP, it's fixed field by Galois. FR, it's fixed field by Galois, FPR by P, and then FPR. And from here, we know that FPR, K is FPR, okay? I'm just say that fact, K is FPR. This extension is the order of the group. An order of the group is greater than or equal to R. Why? Because it has a subgroup containing order R. So it is greater than or equal to R. It has a suborder. Therefore, the group is either same as subgroup or it has more elements. We don't know. Right. Now we use the field extensions. Okay. Now we use the top of this field FP. Okay. I'll write now K. This is my K. K is to Kg. Kg is to K. This is nothing but this is my F. This is nothing but K is to F. But K is to F is the whole extension which is degree R. This is nothing but R. However, this is greater than equal to R. Can it happen? No, it will only happen if we have K is to Kg is equal to R and Kg is to F is 1, which implies your fixed field of Galois group is nothing but finite field Fp. Right? And you will also get that your Galois group is actually equal to R. That means, let's going back, the Galois group cardinality. Look at the definition. Galois group cardinality, so it is R. Index is also R. Therefore, this is a Galois extension. This is a Galois extension. This requires little bit work. For finite field, things require some work. Now, the four will, because we have to cover some more questions, so I'll be little. Okay, let's go to fourth part. Okay, Galois group of Q 2 power 1 by 6 is to Q is all those mapped from Q 2 power 1 by 6 to 2 power 1 by 6 such that they Q fixed. Now look at them. Notice Q 2 power 1 by 6 to Q. First of all, the degree, okay? Degree is how many? It's 6, right? Because x power 6 minus 2 is reducible to Q. Knowing this fact, the degree is 6. We want to know the order of the group. Is it more than 6 or less than 6? More than 6, we know it's never there. But you can see that the Galois group can be either less than 6 or equal to 6. Let's check what is that. So from this to this, we need to map where does 2 power 1 by 6 goes. Again, you have many times you have seen this should be like 6 roots of unity are multiplied with this, and you will get all such choices. But important fact is among them, since you not go outside this field, this is a real field, you just have to find out how many are the real elements. How many elements, if you see from this product, how many are the real elements, not the complex one. Notice if K is 3, then only you will get a real root, which is nothing but E pi I. 2 power 1 by 6 E pi I, which is nothing but 2 power. So 2 power 1 by 6 and minus 2 power 1 by 6 are the only possibilities. There's two homomorphisms. 2 power 1 by 6 to 2 power 1 by 6. Then going to either you fix 2 power 1 by 6 to itself, or you can map to its negative of that. Right? So either you can go to 2 power 1 by 6 goes to minus 2. So the group cardinality is 2, only 2 homomorphisms we have. However, the index is 6. So therefore, this is not a Galois. This is not Galois. I think this should be clear enough now. That what are the extensions, what are Galois extensions, what are their fixed field, how to get the group of automorphisms with that fixed. So all those things I think now more or less are clear. Now look at this. Recall a theorem which we have seen in the um, lecture, that if we have a finite extension K over F, let's say we have K over F is a finite extension, and if F is an irreducible polynomial which has root in K, then F splits completely if and only if K is the splitting field of polynomial. Right? So important fact here is that the polynomial has to be irreducible. So if somebody asks you that if Q root 2 does not satisfy above result if Fx is this. So if we take Q root 2 over Q as a finite extension, yeah, it's a finite this polynomial which has a root, right? Which has this root, Q root 2. Root 2. It has a root. But if you can see, my claim is that it does not split completely. What is the issue? What is the issue that it does not split completely? The issue is your function, your map is actually or is not an irreducible function. So it's not irreducible over Q. Therefore, clearly, it cannot split completely in Q root 2. As you can see, plus minus I are also roots which does not belong to Q root 2. In Q root 2 I is the splitting field. So therefore, this case does not apply to our theorem because your function is itself not irreducible. So here this fact that if you have an irreducible polynomial which has one root in your field, it will completely split in your field. But that will only happen if your function is irreducible. I think it's okay what I want to say. Now, okay, I'll just rub off solutions. Okay. Next question says when finite extension is normal. Yeah. Think for a minute what are normal extension. Okay, so if you can recall, then extension A over F is normal if and only if whatever element you choose from K, the irreducible polynomial. So actually the conditions that we have written in the previous theorem, any of them, if it is clear, if it is there, yeah, so either this statement or this statement, if it is there, then we say the extension is normal. Or maybe I'll rewrite the irreducible polynomial. It's completely in K. So, yeah. So whatever you take an element from K and you take its irreducible polynomial, that should be splitting completely in K itself. I guess it's more or less clear. Now, knowing the definition, let's check what I first of all give examples of normal extension. Can you give? Simple enough. Hmm? Yeah, so big to extend, if you look, this is or this or this, they all are normal. They are simple examples of normal extensions. Why? Because if you take for root 2, let's say, this irreducible polynomial is x square minus 2. and roots are plus minus root 2. Both lies in your field, right? So therefore it splits completely and therefore your extension is a normal extension. Second part says that q 2 power 1 by 4 over q. What can we say about this? Is it, yeah, is it normal? Is it normal? Think for a minute, you'll get your answer. So my claim is that this is not normal. Can you think for a minute that why it's not normal? All right. So if you look at 2 power 1 by 4, this is an element inside your, and result says for any element alpha, I have chosen this as alpha, its irreducible polynomial, which is this, should split completely in the field. But note that the roots of f are 2 power 1 by 4 minus 2 power 1 by 4. We have seen several times, so I'm just repeating. Minus 2 power 1 by 4i. Does all root lie in your field? Clearly no, right? Because these two does not belong to your field. Therefore, it's not a normal extension. So now you have an example of an extension which is not normal, and also you have example which are normal. Right? Now you should see the difference, which are normal, which are not. All right, so now looking at this, we will go to the other question. Find the Galois group and determine if the extensions are normal Galois. Okay, we will see these now. Okay, I will just simply above the solution so that we can discuss the solution now. Right. So Galois group, remember we want to know K is to Kg, the same as mod G, then we say K or maybe K is to F is Galois if and only if this is same as this. F is Galois. Recall this is a statement. Normal we have just now saw. What about the first one? Q 2 power 1 by 3 omega over Q. Is it a normal extension? For normal, whatever alpha you choose from your field, look at its irreducible polynomial fx such that alpha is a root. Then f should split in Q 2 power 1 by 3 omega in order to say the normality. You choose, okay? So if you see yourself, the elements that it contains is 1, 2 power 1 by 3, 2 power 2 by 3, omega, 2 power 1 by 3 omega, 2 power 1 by 3 omega square, 2 power 2 by 3 omega, 2 power 2 by 3 omega square. Right. However, some of them are like contained in the other, so I will simply write them. Right, like this, we have elements in this. You choose any. Okay, let's you alpha 2 by 1 by 3 omega. Suppose you choose this as an element. Can you tell me the irreducible polynomial which being satisfied this, where omega is the cube root of unity? The primitive root, third root of unity, in fact. Yeah, so if you see, it will be nothing but x cube minus 2, right? This is irreducible. This is irreducible over Q. Right? What can you say about this? The roots possibly, roots are this, this, and this. But all the roots lie in your field. Exactly, right? If you see any other alpha, let's say 2 power 1 by 3, omega is cube minus 1, 0, it has root 1, omega, omega square, all these lying in your field, right? So indeed, this is a normal extension. Indeed, a normal extension. What about Galois extension? So for Galois, you need to know the degree of this field should be equal to the group of all automorphism which fixes Q over Q to power 1 by 3. Okay, just put this. What can you say about this? The degree. This you saw, this has degree 3. And here you are just adding omega. What is? Adding this field with omega. This is anyway, let's say K prime. This is like K prime, which does not contain omega. And if you have, let's say, K prime omega over K, where K prime contains Q, okay? It's like Q 2 power 1 by 3. So what is that irreducible polynomial? Satisfied by Q. Omega satisfies this polynomial. It's a cube root of unity. However, this is not irreducible. The irreducible polynomial is this. And that will be reducible over this field also. So the same polynomial will be reducible this. It has degree 2. This is 2. Notice their degree is not 3. Right? Here it is 2. The degree Q 2 power 1 by 3 omega is to Q is 6 degree extension, not 9. Somebody may think over this as 3, but this is not 3. It's degree 2. All right, so we have 6 degree, 6 degree extension over Q, which is Q 2 power 1 by 3 omega. It is a Galois extension. Notice for Galois, you have to look at the Galois group of Q 2 power 1 by 3 omega. That means all automorphism from your field to the field. Right? Oh, okay, maybe let's add a page and then do calculation there. So we want sigma from Q 2 power 1 by 3 omega to. Here, generators are there. You only need to know where these two things go. It's enough to know this, right? So think for a minute and write down that where 2 power 1 by 3 can go and where omega can go. Notice omega is the primitive root, therefore it's not, and therefore it's irreducible polynomial. It's a repetition, okay? All right, so 2 power 1 by 3 can possibly go to 2 power 1 by 3 omega square. I think we have seen this several times. But omega, irreducible polynomial, this, which has root only omega and omega square, which is minus. Oh, I'm so sorry. Not equal to. Okay. We have property like this. The square you can say is minus 1 plus 1. Yeah. All right, so we have either omega can go to omega or it can go to omega square. So total 2 power 1 by 3 has 3 choices. Omega has 2 choices. So total homomorphism will be 3 into 2, 6 many. I'll write explicitly this go to this go to this identity. 2 power 1 by 3 go to 2 power 1 by 3 omega being fixed. 2 power 1 by 3 going to 2 power 1 by 3 omega square omega fixed. 2 power 1 by 3 going to 2 power 1 by 3 omega 1 to omega square is going to this, but omega going to omega square. This, but omega to omega square. So these are total. But our Galois group, sorry, our index over of our extension, or let's say degree of our extension, is 6. Therefore, the same as Galois group. Therefore, it's a Galois extension. This is indeed a Galois extension. All right, so I think things are clear now. Next, saying that any degree to extension of Q, is it normal and Galois? Can we say that? Yeah, can we say any degree to extension over Q is normal? But Galois. For a minute, I think it has been more or less in the lecture class. I will repeat that. Okay, indeed, that is normal and Galois both. Why? Let's look at the proof now. Any degree to extension over Q, in fact, in changing Q by characteristic, any characteristic zero field, we still say that any degree to extension is a normal extension. Why? We will see. And in fact, it is a Galois also. We will see that also. You know that any have extension over Q degree 2, then you can write it as isomorphic to QS by the polynomial f, where it has degree 2 and f is irreducible over Q. This fact we know. We'll use this fact. So let that polynomial is this, which is irreducible. So this is our irreducible polynomial of degree 2, let's say. And suppose alpha be a root. We want to know if alpha is a root which lies in F, then the other root should also lie in F. This is what we want to prove in order to say it is a normal extension. So suppose alpha be any root, that means this should hold true. This should hold, right? If that holds, then beta, suppose beta is another root, right? We want to know this belongs to F or not. When sum of the roots is the negative of the coefficient of your polynomial, right? This is your polynomial, sum of the roots is minus a1. Right, so beta is nothing but, beta on this relation is nothing but a1 and alpha, both lie in Q and Q alpha, right? So suppose your F is nothing but Q alpha, which contains alpha as a root, suppose. And here you also know that beta also belongs to Q alpha. Let's say it is F. That means your F can be seen as Q alpha, which contains both the roots, and therefore your polynomial splits. Notice that alpha not equal to beta. You are using this fact. You are using this fact to say alpha plus alpha not equals to beta. And in fact, characteristic 0 for characteristic 0, this is true. This is true for characteristic 0, however, not true for this proof doesn't work because of for a finite field, because this may be false for a finite field. However, this is true for characteristic 0 field. Therefore, the roots are distinct and both lies in your extension field. Therefore, your extension is normal. Now, why Galois? Because extension is degree 2, that you know, degree 2 extension. Now you need to know the Galois group. Group of automorphisms are 2. How many automorphism is that? That many roots you have, right? So where will you map to? Alpha going to alpha is one automorphism, right? So one field homomorphism. But beta is another root. So you can map alpha to beta. So again, the group has order 2. Therefore, this is Galois. So in fact, any degree 2 extension over characteristic 0 is a Galois and normal both. This Galois plus normal. What can we say about a degree 2 extension over a finite field FP? Sorry, a characteristic P field, not finite field FP, but any characteristic P field. Can you say degree 2? It was characteristic 0 where the result is true. But can we say degree 2 extension of a characteristic P field is also Galois and normal? If you think, you will get the answer is no. And if you see example is this. Okay. So it's a characteristic P field that you can see. And this you take an extension FP root T. FP root T. Just like you have Q root alpha, that's it. Q root 2 over Q. Just like that. You are changing Q to be FP T. This is the field of all such quotient of such polynomials FT, GT by FT and GT both are FPT and such polynomials, like such polynomials. Okay, it is a quotient field actually. Notice root T is in this and therefore product is also in T. Therefore this contains T. This T is belong to this field. Therefore there is an extension. That means it's a containment. There is a containment. That's why there is an extension. Otherwise, how it is an extension, right? So T belongs to this, therefore it's an extension. Right. Now the irreducible polynomial of your root T over FPT is nothing but x square minus T. It's simple to see, right? So therefore the degree of your extension is 2. So we do have an extension of degree 2 over characteristic P field. Now can we check for this particular field, is it a normal extension and is it a Galois extension? These are two questions now. Right. Let's look at its polynomial. X square minus T is the polynomial. Its roots are root T and minus root T, and both roots lies in your field. Both roots lies here. Root T also belong, minus root T also belong. Therefore, indeed, it is a normal extension. Roots lies, right? But is it Galois? Well, it is not Galois. Why? Because if you try to see its minus root T and root T two roots, choice of root T is 0, right? Because 2 is the characteristic of your field. If I take P to be 2, if I take P to be 2, then 2 root 2 is 0. T plus my root T equal to minus root T. Can we say that? Both the roots are actually same. So your characteristic polynomial, irreducible polynomial, irreducible polynomial is actually, it's a square of a polynomial. The square of a polynomial. Both the roots are same. So if you try to define automorphisms from group to group, so from field to field, then root T to root T is the only possibility, because root T to minus root T, this possibility is no longer a different possibility because this is same. So therefore, only identity automorphism is the map which you have. Therefore, the Galois group has cardinality 1, but your extension field has cardinality 2. So FP root T is to FP T is 2. However, Galois group is 1. Therefore, this group cannot be a Galois. The extension cannot be a Galois extension. It's not a Galois extension. I think more or less it's clear what is happening here. Now we will go to question number. This was question number 10. So question 10 is done, more or less. We will go to question number 11. Okay, I'll just something otherwise. Yeah. Question is, what is the question first of all? K over L over F is the field, and if K over F is normal, that means this is normal if this is given to us. This is normal given. Can we say this is normal or not? Think for a minute and try to see that whether it is normal or not.
So, but I will give you an example saying that this need not be normal in general. In general, so if you look at Q, 2 power 1 by 4 I, or 1 by 4 and Q, or right, Q 2 power 1 by 3 I, Q 2 power 1 by 3 Q. Both the examples will serve the purpose. Example, is this normal? This is normal, right? You can check. Is this normal? Normal. Check. But is this normal? But is this normal? Right? It's no, because x power 4 minus 2 does not split completely here. Same here. X cube minus 2 does not split completely. Although it has one root completely in q2 power 1 by 3. It has one root, 2 power 1 by 3, namely this, but does not have all roots, therefore not normal. So in general, this lower one is not normal. If your big one is normal, your lower one may not be normal. I mean, if I give you several other examples like q root 2, root 3, q root 2, q, in this case, this is normal. If you look at root 2i, again it's normal. But still we have examples where it is not normal. So it depends. It depends. In general, it's not a normal extension. All right, so this is one more question. We have q root 2i over q root 2 over q. And just rub off the answers. This is a question that you have given a tower of fields, and first of all, you have to check k over L, L over F, K over F are these normal extension. That means this, and this. All three extensions, which of them are normal and which of them are not normal? Think for a minute. Okay, so you can see that x square minus 2 x square plus 1. For this, you have x square minus 2. For this, you have x square plus 1. These are the irreducible polynomials. And therefore, degree 2, here it is degree 4. And for 2, you don't even need to check. Why? Because we saw any degree 2 extension over a characteristic 0 field is always normal. Both these are characteristic 0. So both these extensions are normal without any proof. Without any proof, knowing the fact that characteristic 0 field over a so yeah, so any degree 2 extension over characteristic 0 is always normal. Is this okay? Same thing you can check for q root 2i. Same thing in the sense this is also normal. Why? Because if you take any this polynomial, its irreducible polynomial is x square minus 2, which splits completely. If you take this element, then its irreducible polynomial is this, which splits completely. If you take the product, then this is the polynomial which will split completely. So all the things are splitting completely inside your field. Therefore, it's normal extension. Therefore, all three are normal extensions. Now, what are the Galois groups? Next question is, what are their Galois groups? Note that if you have a degree 2 extension, its Galois group can be, it's either trivial group or it can be the whole of groups, 2 degree 2 group. I mean order 2 group, which is C2. So notice that for them, this is also C2 or maybe Z2, Z2. In fact, for L over F is also it is Z2. But for this group, we have seen maybe several times, or maybe the example which might have come before, it is Z2 cross Z2. This we have seen, I guess, a similar stuff maybe. Question is, can we see an exact sequence from 1 to Galois group of K mod L, Galois mode of K mod F, Galois group of L mod F to 1? Is there exact sequence? That means, can you embed Z2 inside Z2 cross Z2? And can you project this to Z2 to 1? That means, can you find phi and psi two maps where phi is injective, psi is surjective, and image of phi is same as kernel of psi? I guess this is the meaning, right? For a short exact sequence, let's right. So, all right. So if you want to see that, let's look at this part. So we will try to embed Z2 inside this and Z2 to Z2 to 1 we will project. How do we define phi and psi? So one map we can define like this. Phi x going to x comma 0, y. Psi x comma y goes to x. The first component, or you can also use the y component. I don't have issue. Or you can define this map as x comma x. Or you can define this map as 0 comma x. There are several ways. But you can check that kernel of this map phi is 0. This is 1, 1. Image of this phi is complete Z2. It is on 2. So both the things are fine. If you see image of phi, this map image phi, then that is isomorphic to Z2, right? Just one copy. You are looking at one copy of your Z2 inside that. That isomorphic to Z2 and kernel is also Z2. So indeed, this map, let me write once again. So you have 1 going to Z2, to Z2 cross Z2, to Z2 to 1 is exact. Why? You take phi from Z2 to Z2 cross Z2, it's going to x comma 0. Or you can define 0 comma x, or you can define x comma x. You can check whether this is a group homomorphism, okay? And you have to define psi from Z2 cross Z2 to Z2. How will you define x comma y? You can either map it to x or you can map it to y. You check, these are easy check that phi is 1, 1, phi is on 2, and image of phi is same as kernel of psi. And therefore your equation 1, let's say, this is exact. This is a definition for exactness, right? All right, so I think this part is also clear about this question. This is clear. Now we will move to another question, that when does a polynomial is separable? Now, since we don't have much time, I'll just see some answers directly. A polynomial is separable if you can write a polynomial is product of irreducible polynomials, and all irreducible polynomials are separable. But they are separable if and only if all its roots are distinct. Right? So basically, a polynomial is separable if its irreducible factors have distinct roots. And extension is separable if every element inside your extension is separable. And element inside field is separable if its irreducible polynomial over the base field is separable. And irreducible polynomial being separable means all its roots are distinct. This is more or less the definition, just the repetitions of things. Now examples. So we saw that this extension at least was separable. Why? Because, can we say why? Because any element from FPR, any element of PR will satisfy this polynomial. And you can check that none of the roots are multiple roots. All roots are distinct. And therefore, you can say that this is a separable extension, right? Just by looking that this is having all distinct roots, you just have to check its derivative is co-prime to it. If you can see that, then you are done. However, this extension, I'm just trying to notice this, I'm trying to show you this. This extension is not separable. It is not separable. Why? Because the roots, if you saw, this is a irreducible polynomial for this element. However, its roots are not distinct. Both were same. First same. Therefore, it is not a separable extension. Remember, this is not a separable extension. Yeah, I think we'll stop here. Rest of the questions on separability, maybe we will discuss more, because separability we have not discussed a lot. All right, so I think I will stop here. Thank you.